This is Unit 2, Topic C, and we're going to begin looking at some shortcuts for finding derivatives. These are going to be what we'll eventually refer to as our basic derivative rules. As we've seen, we have a way of analytically or algebraically calculating a derivative, but it's a fairly lengthy process. So if we could see some patterns that we could use to form shortcuts, it would help us to find derivatives a lot more quickly in the future. So let's start with linear functions. If I have a linear function like f of x equals 3x minus 2, of course we all know the slope is 3, and since the slope is the derivative, that means the derivative is also 3. Another linear function, this one has a slope of negative 2/3, and therefore the derivative must be negative 2/3. If you have a constant function, we can think of this as 0x plus 7 if we want to, right? It's horizontal line, or the slope of 0, meaning the derivative would have to be 0. So, in conclusion, we can say that anytime we have a function f of x equals a constant, like this one, the derivative will always be 0. And if we have a linear function, f of x equals kx, k is our slope, and so our derivative here would be k. So at this point, any constant or linear function, we don't have to go back to that definition of the derivative. We can just use these as shortcuts to find the derivative quickly. It would be nice if we could actually do this maybe first of all for any power of x, not just a first power of x, because that would lead us to being able to have a shortcut for all polynomial functions. So the next thing we're going to take a look at here is how do you find the derivative of a power function, x to the n power. So let's begin by using our definition of the derivative on the function f of x equals x to the n power. Remember, f prime of x is the limit as h approaches 0 of f of x plus h minus f of x over h. And so for this function, we will have x plus h to the n power minus f of x, which is just x to the n power, over h. Now, this was all not a problem when we had an actual value for n, because we could actually do x plus h squared, or x plus h cubed, or to the 4th power, or whatever we needed. But now that we've got a general n for our exponent, we have to think a little bit more about how to handle that. In order to do that, I'm going to ask you to take a look at some powers of x plus n that I've actually already got written out for us here. This one we're certainly familiar with, x plus h squared. Right? And this one we did together in the last video, or a couple of videos ago, x plus h cubed. And then I just wrote out x plus h to the 4th here as well. I just took x plus h and multiplied it by all of this, and did all of the algebra, and came up with that result. I'd like to start by looking at the patterns that are being established for the powers of x and h. Notice that the x powers start here with the highest power, the 4, and they go down. The next term is an x cubed, and then an x squared, an x to the 1st, and then finally no x's at all. The h's go exactly the opposite. There are no h's in the 1st term, and then the 1st power, 2nd, 3rd, and 4th powers in the subsequent terms. So the powers on x and h are very predictable in the way that they work. Same idea you could see up here, right? So if I could figure out a way to predict these coefficients, I would have a really predictable way for doing x plus h to any power. In terms of predicting the coefficients, we use something called Pascal's triangle. This is what it looks like. X plus h to the 0 power, of course, would just be 1. Right? And x plus h to the 1st power is just 1x plus 1h. So I'm just going to put the coefficients, 1 and 1, in what I'm starting to build as a triangle. X plus h squared, up here, the coefficients are 1 and 2 and 1. And again, I'm kind of building this in a triangular pattern. X plus h cubed, right here, my coefficients were 1, 3, 3, and 1. And then the fourth power, 1, 4, 6, 4, and 1. So what we're looking at here in terms of a pattern is to go from one row of Pascal's triangle to the next. Notice that what you can do is add. 1 plus 1 gave me 2 here. 1 plus 2 gave me 3 down below. 3 plus 3 gave me 6. 3 plus 4 gave me 1, and so on. So if you kind of see that pattern, we could actually predict the next row here. We always start with a 1. 1 plus 4 would say 5 comes next. 4 plus 6 would be 10. 6 plus 4 would be 10. 4 plus 1 is 5, and we always end with a 1. And so if I wanted to write out x plus h to the 5th power, I could do that without doing all that multiplying. I'm going to start out with 1x to the 5th. My next coefficient is 5. I'm going to reduce the power on the x and increase the power on the h. Next coefficient is 10. Bring down the power to x cubed. Bring up the power to h squared. And continuing, my next coefficient is 10 again. This one would be x squared h cubed. Next coefficient is 5. X to the 1st, h to the 4th. And then the last coefficient is 1. We're done with the x's, and we'd have h to the 5th power. So if you kind of see how this Pascal's triangle works to predict these powers of x, we're going to go back to our definition of the derivative, and we're going to use kind of what we've learned here to see what we can do to simplify. All right, so x plus h to the n. We know that the first coefficient in every single row was always a 1. So we're going to start out with 1x to the n power. Now notice that the second coefficient in each row was always the value of the exponent, right? When it was the 4th power, this coefficient was 4. When I did the 5th power, this coefficient was 5, and so on. So when I've got an nth power, I have n as my next coefficient. I have to reduce the power on the x, so that's going to be now the n minus 1st power, and increase the power on the h, so I now have an h to the 1st. We would continue on that pattern, and although using combinations it's actually possible to write down a formula for each coefficient, I'm not going to bother, and you'll see why in just a little bit. I'd have some coefficient here, and then I'd have x to the n minus 2, reducing the power on x, and h squared. Right? And that would continue. I'd have another coefficient. I'd keep on going down in powers of x and up in powers of h. Finally, at the end, right, we always ended with a coefficient of 1, and we have h to whatever power, so we'd end with an h to the n power here. So that's the x plus h to the n. I also have a minus x to the n, and then that's all over h. All right, we did all of that to get two things to happen. X minus n and the opposite, or excuse me, x to the n power minus x to the n power gives me 0. I can get rid of those. And then notice that all of the remaining terms have an h in them. h squared, it would go up to h cubed and h to the fourth, etc., all the way to h to the n at the end. So I'm going to go ahead and factor out that power of h as I go. So factoring out at h, I'd have n x to the n minus 1 h is factored out. I'd have something x to the n minus 2, and that'll become an h to the first, and so on and so on, and then the last term would be h to the n minus 1. All right, that's the second thing I did all this for, right, was to divide out those h's, which means we no longer have the problem with 0 in the denominator. And I should be able to just plug in h equals 0 now. So I have n x to the n minus 1 plus something times x to the n minus 2 times h, which is 0. And now you can see why I didn't really care what that number was, because I'm going to multiply it by 0 anyway. The powers of h just keep on getting bigger and bigger and bigger here through here, right? So we're going to keep on adding zeros all the way through until we finally get to 0 to the n minus 1 at the end. All of these terms will have multipliers of 0. And the only non-zero term I'm going to end up with is n x to the n minus 1. So that's a pretty nice shortcut. Anytime I want to take the derivative of x to any power, the derivative is going to have the power brought down here as a coefficient, and then the new power will be one less. Let's write that down as sort of a formula on our next page. I left us some extra space because usually I do all that multiplying stuff out in class, but I figured if I pre-did it for us, it would make this video a little shorter. All right, so for the function f of x equals x to the n power, the derivative is n x to the n minus first power. And we're just going to practice doing that a little bit. So for x squared, the derivative, my power of 2, I bring that down now as the multiplier, 2. And then I'd have x to the 2 minus 1, or first power. And I just get 2x to the first, or 2x. We did that one all the way out a couple of videos ago, so that one's not unexpected, but you can see how our little shortcut here works out really well for us. Let's try x cubed. N is 3, so I'll start with 3, and then x to the 3 minus 1 power gives me 3x squared. Same idea with x to the 4th. The 4 is the n, so I start with the 4, and then x to the 4 minus 1, or in other words, 4x cubed. So you can see how you can do any power of x very easily using this pattern. Even when we have things that don't initially look like a power of x, we often can rewrite them as a power of x so we can take further advantage of this nice rule. What about the square root of x? Well, of course, you know that you could write that as x to the 1/2 power, and if we apply the same rule to that, n is 1/2, so I'd have 1/2 times x to the 1/2 minus 1, or 1/2 x to the negative 1/2. Now, of course, you could rewrite that as 1 over 2 square root x if you want to. Oftentimes, fractional exponents are easier to work with, actually, than the radicals, but whichever one works better for your particular situation. One more example similar to that. 5th root of x cubed is actually x to the 3/5. And so if I use my same rule here, n would be 3/5, and the new power would be 3/5 minus 1. So I'd get 3/5, x to the negative 2/5. X in the denominator, it's still okay, but you do have to rewrite again as x to a power. This rule only works when you have just plain old x to a power. That x can't be anywhere else. So I have to rewrite this as x to the negative first before I can apply my rule. And now n is negative 1. So I'd have negative 1, x to the negative 1 subtract 1, or minus x to the negative 2. Again, if you wanted to, you could go back to something like negative 1 over x squared, but again, negative exponents are fine and often easier to work with algebraically. Same idea here. 1 over x to the 4th could also be written as x to the negative 4th. So now with an n of negative 4, I get negative 4 x to the negative 4 subtract 1, or negative 4x to the negative 5th. So there's our power rule, a nice, really great shortcut for differentiating x to any power. We will pause there and come back and take a look at some other types of, well, actually, you know what? Let's not pause there quite yet now that I think of it. Let's take a look. I wanted to go back to those graphs that we drew in the last section. And let's in particular look at these first couple. This one we had already seen graphically, but what about this one? This cubed function. The derivative was a squared function. And I just wanted to point out to you that when we did this graph isn't exactly x cubed. It's probably got some more stuff with it. But notice that with a cubic polynomial, we predicted the derivative to be like a parabola or a second degree polynomial. So that idea that whatever our original function is, degree 2, the derivative is 1 degree less. Second degree parabola, first degree line. Third degree curve, second degree derivative. So we've kind of seen this a little bit in the graphs that we were investigating earlier. All right, there we'll pause and come back and look at some more of these in the next video.